In this video, we're going to look at yet another volume of a solid of revolution example. Just in this case, we're going to be rotating around a vertical line rather than rotating around a horizontal line. So we've got y equals x, so it's this diagonal line. Y equals 0 is our x-axis. Vertical line x equal to 2, vertical line x equal to 4. And instead of rotating around the y-axis, we're going to rotate around the line y equals 1. Excuse me, x equals 1. All right, so when we integrate, or excuse me, when we slice here, since we're rotating around a vertical line, we need to slice perpendicularly to the axis of rotation to make a circular washer or a circular disc. It's the only method that we have right now. So slicing perpendicularly to the to the axis here that's a vertical axis means we're really slicing up the y-axis. If we're slicing up the y-axis, that means we have to integrate with respect to y, means everything needs to be in terms of y, not in terms of x. Okay? All right, notice in this case, just like when we did with the area problems, we've got an issue here where our right curve is the same all the way through, but our left curve changes halfway through. So to be able to do this volume in this case, we're going to have to use two integrals. All right, so this first picture here is just showing what the solid should look like for us. We'll have this little cylinder in the middle. That's what this line getting rotated around is. We'll have the slanted piece here, which is what this piece is getting look like when you rotate that piece around the vertical line. And then you get the big cylinder on the outside. So when we slice here, this is what our washers look like. We'll have two different cases, right? We're going to have a case where we've got big cylinder minus little cylinder is what's giving us our washer, versus we'll have big cylinder minus this bowl-looking thing, and that gives us our washer. So again, we're going to have two integrals that we'll have to do to be able to do this volume. All right, so we'll have to split it to 2. That's the y value here where our left bounding curve changes. So we'll have an integral from 0 to 2. And an integral from 2 to 4. We have washers in both cases, so I need a big radius minus a small radius in both cases. As we go from y equal to 0 to y equal to 2, our right bounding curve is 4 and our left bounding curve is 2. However, remember we're rotating around the line x equal to 1. So our radius, big radius, will be 4 minus 1. Right. Remember, it's distance from axis of rotation to the curve. The curve is 4. The axis of rotation is 1. So we're going to have 4 minus 1 for that radius. Okay. For the smaller one, we've got 2 minus 1. Okay. So here's our big radius. Here's our small radius. And we have to square each of those because, again, remember, we're doing areas of circles. Area of a big circle minus area of a small circle gives us the area of the face, and then multiply by the thickness. From 2 to 4 now, our left bounding curve changed. But again, to find our radius, we're going to go from axis of rotation to the curve. Axis of rotation is at 1. The big curve here is 4, the one that's farther away. So 4 minus 1 will be our big radius. For our smaller one, we need a function of y. So we'll have x equals y here. So we'll have y minus 1 is our smaller radius. Do some housekeeping on your integrands. Do antiderivatives. So we'll get an 8y here for the first one. The second one we'll get a 9y minus a 1/3 y minus 1 cubed. Plug in our endpoints. When we plug in our endpoints for our first one, we should just get a 16. In the other one, we'll get plug in 4 for y. That makes that a 3, right? Because we have 4 minus 1 there. Plug in 2 for y, we get an 18, and that makes that 1 there. Do all of our simplifying of our arithmetic, and we should get a final answer of 76 pi over 3.